Hello students, this is Mr. Allen, and today we're going to look at section 6.1, which is on area between two curves. Our objectives here are to find the area of a region bounded between two curves using integration, and to find the area of the region between intersecting curves using integration. With a few modifications, we can extend the application of definite integral from the area of a region under a curve to an area of a region between two curves. Consider the two functions here in this graph. We've got function g and we've got function f that are both continuous on the interval from a to b. Also, the graphs of both f and g lie above the x-axis. You can geometrically interpret the area of the region between the graphs as the area of the region under the graph G, subtracting the area from under the graph F, as shown in this diagram. So we've got the top function here. This is the F function. And then the bottom function, this is the G function. So if we're trying to figure out what the area is between those two curves, the way we can do that is take the area of what's under the graph of F, that's the middle picture, and then we look at the area of what's under the graph of G, that's the picture there on the far right, and then what we're going to do is we're going to subtract those two quantities. So we're taking the whole area minus the lower area. That's going to give us the area in between the two curves. And so this gives us our definition of the area between two curves. If f and g are continuous functions on the interval a to b, and we know that g is less than or equal to f for all of the x in that interval, then the area of the region bounded by the graphs of f and g and the vertical lines x equals a and x equals b is area equals integral from a to b of f of x minus g of x dx. In figure 6.1, the graph of f and g are shown above the x-axis. This, however, is not necessary. The same integrand, f minus g, can be used as long as f and g are continuous and g of x is less than f of x for all x in the interval. So for example, look at the graph here on the left. Here we can see that the f function is clearly greater than the g function, but notice that the g function is slightly below the x-axis. That's okay. Or look at the graph here on the right. Here both functions are below the x-axis. You still can take f of x minus g of x in the integrand. So let's look at an example. We want to find the area of the region bounded by the graphs of y equals x squared plus 2 and y equals negative x, and our a value here is going to be x equals 0 and our b value here is going to be x equals 1. So first let's look at the graph here on the right. The parabola, the first function, y equals x squared plus 2, we'll let that be f of x because that's the function that's greater, or sometimes I'll just say it's the higher function. And then the second function, y equals negative x, of course, that function is below the f function, so we'll call that one g of x. We're trying to find the area between those two curves going from 0 to 1, and so now we've got everything situated the way we want. And so we can go ahead and use our formula. The area is simply going to be defined. And by the way, here we're talking about the delta A. We're talking about, in this example here, we're using this representative rectangle. I don't know if you can see the little blue rectangle there. That rectangle has the distance from F down to G, and then its width is, if you will, delta X. So we're going to call that delta A. That's the change in the area is equal to F of X minus G of X delta X. So now we can just plug in f of x, which is x squared plus 2, g of x, which is negative x. We can now use our formula for the area of a region, which is integral from a to b of f of x minus g of x. And now we just plug in our change in a, or delta A. We're going from 0 to 1. We can clean that up by just using the distributive property here. and then integrating, okay? So we would have x squared plus x plus 2, and then, of course, when you integrate that, you're going to get x to the third over 3 plus x squared plus 2x. And, of course, when you plug in 0, you get nothing. When you plug in 1, you get 1/3 plus 1/2 plus 2. So the area between those two curves is 17 over 6. That's the exact area between those two curves. In example 1, the graph f of x equals x squared plus 2 and g of x equals negative x do not intersect. They do not have any points in common. In fact, so what I'm talking about here is if this is my y-axis and this is my x-axis, and we have, that this was that x squared plus 2 function, which I think we called f of x. And then down here, we had our other function, which was something like this. And this was our g function, which was, I believe, negative x. Those curves do not intersect. So the values of a and b have to be given explicitly, because we could literally pick any values a and b. A more common problem, and this is our second objective, is to find the area of two regions bounded by intersecting graphs. In this case, and this is the important part, you will have to calculate the intersection of a and b. You will have to figure that out algebraically. So here we have a very similar problem. F of x equals 2 minus x squared, and g of x is equal to just x. So this is very similar to our first example. Now look at our graph. Here we've got a parabola that opens down, and now we've got the graph of y equals x. Notice that the graphs of f and g have 2 points of intersection. You are going to have to figure out what those points of intersection are. You're going to have to figure out what the x value is at first, and you're also going to have to figure out what the x value is over here on the right. Now, this is a pretty easy example. So how would you do that? Well, hopefully you remember from Algebra 1 and Algebra 2, we're just going to set these two functions equal, and we're going to solve the equation. So 2 minus x squared, this was our f function. And then our g function here was x. So we're just going to set them equal. And we're going to go ahead and subtract the x over to the left. Now we've got a general form of a quadratic equation. We can factor that. So we're going to get negative quantity x plus 2 times the quantity x minus 1. Now we use our zero product property, which tells us that x is equal to negative 2 or 1. So we now know that on that graph on the last page, the x value where they intersect was negative 2, and the other x value, I'll call it x sub 2, was 1. So that tells us what our a and our b are going to be for this problem. So again, we're going to let the change in the area just be f of x minus g of x. We've already established that the f function is greater than the g function. So we can go ahead and plug those items in. Now we're going to use our formula. We've just established that a is negative 2 and b is 1. Here's our f function. Here's our g function. We're minusing these two guys. That's what the formula tells us to do. So now we're going to go ahead and integrate. And you can see that we basically are using essentially the exact same integral, a nice easy one that we used on our previous example. Now we're integrating from negative 2 to 1. And we will get an answer of 9/2. So how this example was different than the first one was you had to figure out what the a and the b is. So this, in addition to doing the integration, you had to figure out what the starting point and the ending point of this integration was going to be. The last thing I want to mention is integration as an accumulation process. The integration formulas for the area between two curves was developed using rectangles as representative element. For each new application in the remaining sections of this chapter, that's section 6.2 basically for us, an appropriate representative element will be constructed using pre-calculus formulas that we already know. Each integration formula will be obtained by summing or accumulating these representative rectangles. So we're going to go with what we know from pre-calculus using our representative element, and that's going to help us develop a new formula. So for example, the area formula for this section was developed as follows. We know that in general, the area of a rectangle is height times width. Then we used, so now we're going to say, well, the change, or the delta of the area, is equal to f of x minus g of x delta x. So the delta x was that width component, that's the width, and the height is the f of x minus g of x. And then we're going to use the process of integration to accumulate or add up those areas. Our final example. Find the area of the region bounded by the graph of y equals 4 minus x squared and the x-axis. Describe the integration as an accumulation process. All right, so here's our solution. We first have to figure out where we're going to start and where we're going to end. Now, this function right here is a parabola, and this particular parabola opens down. And we also hopefully remember that from pre-calculus or algebra 2 that it has zeros at 2 and negative 2. So that's why we started at negative 2 and we're going to end at 2. You can think of the integration as accumulation of the area of the rectangles formed with the representative rectangles from negative 2 to 2. So what we're talking about here is if we were to draw a little rectangle like this, the width of this rectangle would be delta x, and the height of the rectangle would be the function y equals 4 minus x squared in this problem. So if we look at our first image here, this is if we integrated from negative 2 to negative 2, which means we're not integrating anything, so we get an answer of 0. We could also, if we look at our second example here, we can integrate from negative 2 to negative 1. That gives us an area of 5/3. We could also integrate from negative 2 to 0, the exact same function. Here we get 16/3. We could integrate from negative 2 to positive 1. That gives us an exact area of 9. That's kind of cool. Or we could just go ahead and integrate over the entire interval from negative 2 to 2 and get a total area of 32/3. So notice what's happening here is we're using integration, if you will, like a function. We are accumulating area as we move from the left to the right. And that's all we have for today.